Hi, everyone. Thank you for joining my talk today. Hope you still have enough energy left after a whole day full of sessions. I'll try my best to keep it interesting for everyone. You can let me know afterwards if it was. My name is Lucía, and I work as a software engineer at InfoSupport, which is a company in the Netherlands. And sometimes I work as a sort of data scientist / machine learning engineer at agency, which is part of InfoSupport. So I have some experience working in AI projects. I also studied computer science at university. And during my master's, I specialized in computer vision, which is a subfield of AI. And both of these experiences, they actually made me distrust AI even more than before. In parallel to this, as I said, I mainly work as a software engineer. And like many of you, if not all, I do use GitHub Copilot, ChatGPT, at my daily work to try to maybe fulfill certain tasks a bit faster or more efficiently. So these two things made me quite interested in the topic of explainability, which is what I would like to talk to you about today. What it is, how we can implement it, and why it is crucial in this current era we're living in with generative AI and so on. So before I start, I would like to ask you if you know what this acronym means. If you could raise your hand if you do. OK, so this one is the most straightforward one. It's not Elon Musk's company. It just means explainable AI. I very much like this definition. It's from the European Data Protection Office. So basically, explainable AI aims at providing clear, understandable explanations for how AI systems make decisions or take actions by trying to infer their underlying rules, underlying mechanisms to make these decisions. And the need for explainable AI has increased a lot in the last years because, the capabilities of AI have improved a lot. And this has accelerated its adoption in the enterprise, especially in more like critical systems. And so most of the times at companies, if you ever worked with AI, to get better performance, more complex models are used, which are basically black boxes. So a black box in AI is basically the same thing as in regular software engineering and in other fields of engineering. So it's a system whose internal implementation we don't know about or we cannot know about. So we can only see, for this input, we get this output, and that's it. And with explainable AI, we can sort of break open this black box. It allows us to justify the output. So for instance, let's say a bank has a loan system, right? It's a typical example for explainability. And you, as a customer, you can request a loan. So if your loan gets denied, an explanation, like explainable AI technique, could let you know maybe, you were denied this loan because your savings were below X threshold, or maybe your salary was also below this another threshold. So explainable AI can make systems a bit more transparent, AI systems more transparent, more fair, and in general more trustworthy. But it can also give us more control over our model because it lets us see how stable it is. So are we maybe getting the similar explanations for similar inputs and outputs, right? If the explanations differ for similar inputs, we know that something might be going wrong. But it can also help us improve the model performance because with explanations, we can maybe see if the model is maybe biased towards a certain input feature. So then maybe we have to redo the feature engineering or maybe increase the amount of training data so that, again, we can improve our model. So now that we've seen the benefits of explainable AI, I think it seems kind of clear why it might be useful, why it might be sometimes essential, depending on the application. But that's not the case for everyone. It's not clear for everyone, let's say. So I wanted to share with you a project that we worked on at InfoSupport a few years ago. It was for an insurance company. They wanted to build a system to predict customer churn. So that's when, churn is when like you want to predict the probability of a customer stopping with your services, right? Like leaving your company, let's say. So we built a model prototype. The performance was quite promising, so they were very happy with it. So they wanted to continue with the project. And at that point, we asked them, would you like to implement explainability? And they were like, no, we don't want that. We don't need that, right? So this is one of the first challenges we have encountered when trying to implement explainability, is that many clients don't care about it. Or maybe they don't know what it is. Or maybe they just don't want to spend time or money on it. In this case, it was because they actually had a plan. So their plan was to run this model on like their list of customers, and then for the customers for which the probability of customer churn was over 90%, they were going to call them, and they were going to do a sort of customer satisfaction survey to find out why they might churn. And then with this data, they were going to do a customer segment, so see like group customers based on their reasons to churn, and then take business actions. Well, I think it's pretty clear why this is not the best idea. It sounds really expensive, like both money and time-wise, like just manually calling everyone. But also in terms of user experience, right? Like imagine if you're a client at some insurance company in this case, and they call you and they ask you if you'd like to do a survey because they think you might leave them. It's not even like, with telcos that when you leave them, they call you and they're trying to convince you to stay. No, they're like, yeah, an AI model told us that you might leave, so what can we do to improve the service? So, in parallel to this, we actually had some budget left for this project, some hours left in the contract. So we decided to implement explainability anyways. So we implemented feature importance, which is one of the most, like one of the oldest techniques, let's say. It basically tells you, how important each input feature is in relation to the output. So you can run it like across the whole model. So as an example, let's say for the bank loan model, right? If the inputs are savings, credit score, salary, like monthly salary, then the feature importance would tell you something like, the credit score is like it contributes 30% to the output, and the savings 60%, and then the what was the other one I said? Salary like 10%. So it's something like this. So we run it over the whole model, but we also run it per customer, and then the output of the explainability technique, we run another AI like machine learning technique, clustering, to do the customer segment. So we basically did the same thing they wanted to do, but with a Python script in a few seconds. Eventually, they confessed to us that their plan wasn't really working because, aside from spending a lot of time in it, customers either didn't pick up, or if they picked up, they didn't really want to do the survey. So they were really happy with what we did, and eventually they used our results to take their business actions. So if you ever encounter something like this, or maybe you're working in an AI project and you want to try out this explainability thing, but your company doesn't want to, or your client company doesn't want to, or maybe even your team doesn't want to, I could maybe suggest to, emphasize the benefits we just covered. Maybe you could tell them about real-world AI systems that failed because of lack of explainability. About this, there's actually this repo on GitHub that I really like. It's called Failed Machine Learning, and it compiles, it's basically like a compilation of large-scale AI projects that failed. It's really nice. Like whenever I feel a bit, demotivated about my work, or something is not really going that well, I check this repo out, and I'm always like, it could always be much worse. And if you start checking the projects there, you will already notice with what we covered until now, that many of them wouldn't have failed if they used explainability, or more like they would have failed before they went public, right? Like they would have noticed that there was a problem. This is an example. It was when Apple decided it was a good idea to create their own credit card, and soon users started noticing that I think it was the like the model to, the credit limit. It was based on an AI model, and they noticed that it was biased against women by a lot. So yeah, eventually they actually completely removed this product. So my unorthodox approach would be, just don't do anything. If a project needs explainability, they are going to realize it sooner or later, regardless of your efforts and time spent in convincing anyone. So that's my first solution. The next one, depending on the kind of project you might be working on, and also if you're based in the European Union. If you're not, you can ignore the next 2 slides. But is the AI Act. So since last year, in the EU, we actually have legislation regarding AI. And if you start reading it, there's an article where it is stated that high-risk AI systems must be explainable. So now you might think, OK, this sounds very niche, like high-risk systems. But actually, high-risk, at this point, it can be anything that processes personal data. So nowadays, I would say almost any AI model you can think of processes personal data. So effectively, this applies to almost any application. OK, so now we know the benefits of explainable AI. We have seen some solutions to implement it. We know it's useful. We know sometimes it's mandatory if we're in the EU, most probably. But how can we implement it? So there are many different techniques, types of explainability, frameworks, also classifications. One that is used very often is this classification. So global explainers are the ones that aim at describing the behavior of an AI model as a whole, so for any kind of input. And a local explainer tries to explain a specific output for a specific input. We saw feature importance before. That's normally used as a global explainer, but it can be used as a local explainer, like we did for the clustering. And a very popular, well-known local explainer is LLM, which stands for, I always forget this name, Local Interpretable Model Agnostic Explanations. So I'll explain it at a very high level, so I might skip some things. If there are any data scientists here, just sorry for this. But so the idea is that you have one input, just because we're trying to explain one specific input and output, right? So one input, and then LLM, what it does is it creates a data set based on this input by slowly perturbing or modifying this input to generate different artificial samples. So in the case of an image like we see here, maybe it could be taking groups of pixels. For text, it could be removing some of the words. For traditional numerical machine learning models, it would be maybe slightly modifying each of the input features. OK, so then we end up with this sort of artificial data set. And then a small white box model is trained on this data. To do so, what we first have to do is all of these artificial data samples, we pass them through the black box model, right? And then we train this new model on these inputs and the outputs from the model. So the goal of this is to get another, they call it surrogate model, to explain the original model based on its predictions. So this sounds pretty useful, but it has quite some limitations. I think the most obvious one that maybe some of you already thought of is that we are training yet another AI model to explain our AI model. And we know that when we train AI models, they're never going to be perfect, right? They're never going to be 100% accurate. If they are 100% accurate, we know we did something wrong. We're probably overfitting the training data or something. But yeah, we're using something else to explain our model that we know that is not perfect. So maybe some of the explanations are right, but we know that it's not always going to be right. There are more limitations, of course, if there are some global behaviors that the model applies to all the inputs, we're going to miss out on that because we're only explaining one specific sample. And also when this artificial data set is created, maybe the created samples don't make sense. Like for an image, it could be fine, it's just pixels, but for a text, maybe if we remove some words, the remaining words might not make any sense at all. So then it's not a realistic example, let's say. So with this, I wanted to showcase, I don't want this session to be like, I don't want to cover every existing technique, that's not the point of today. But I wanted to use this one as an example of how, like to show that implementing explainable AI is not trivial. Like there are options, but they have limitations. And this is something that also not everyone knows. So I want to share another project we worked on. This one was for a blood testing lab, and they wanted to create a model to predict the risk of severe bleeding in thrombosis patients. So we again worked on a model prototype. The performance was really good. They were very excited about it. So they greenlighted the project. And we asked them the same exact question as before. Would you like to implement explainability? And they were actually quite surprised with this question because they assumed that if you train an AI model, you can always understand how it works. They didn't know about this explainability thing. They just thought that that would come out of the box, let's say. So this is another challenge we have encountered. It's sort of in the extreme opposite side of the challenges spectrum compared to the other project, I guess. But there is actually one solution to rule them all challenges, and it's this one. Does anyone know what this acronym means? Okay, no one, okay. Okay, so this stands for Interpretable AI. So we saw it a bit in the LIME technique. So it's basically a white box model. It's a model that is inherently transparent, that when it's trained, we can actually see the rules that it has learned from the data. A couple years ago, some of my colleagues worked on this internal framework. They call it AutoExplain. And it's basically an AutoML framework. So AutoML is when instead of having a data scientist choosing a model and tuning the hyperparameters and everything, you just have a framework that automatically trains a ton of models with a ton of combinations of hyperparameters, and then it chooses the best performing model based on the performance metrics we choose. So they implemented the same idea, but they only trained interpretable models. And they also chose the final model not only based on the performance, but also based on the transparency. And at the time of this project, there was no way to measure explainability or transparency. So one of my colleagues came up with these two metrics. The first one is compactness. So let's say like the explanations of a model are compact if they can portray all the relevant information with the lowest number of features, so that it's more like human understandable. And stability. This we covered a bit during the benefit. So stable explanations are explanations that for similar inputs and outputs, similar explanations are given. Again, I don't want to I would talk about this the whole day, but we don't have time, so I won't share the math behind it. But if you're interested in this, the framework is sadly not open source, but my colleagues, they wrote a research paper which was published as part of the proceedings of an XAI conference. So this one is public, so if you're interested in it, if you want to implement it yourself as well, everything is reproducible, so just feel free to note down the title. Okay, so now it seems that all of our problems are solved. With interpretable AI, we don't have to worry about any of the challenges because we don't need to convince anyone. We don't have to worry about the AI Act because our models are already transparent. Well, this was only until LLMs appeared. So LLMs, as you know, are deep neural network models that can understand human language. Of course, they cannot, but let's call it like that. And they can generate human language. And they do so by finding patterns in text data, large amounts of text data, and calculating the probability of a word following up on another word or another series of words. So as much as LLMs seem to us like smart chatters, in the end, they're just statistical models. They're word predictors. LLM, as you all probably know, stands for large language models. They're called large because they are indeed very, very large. They're a collection of billions or sometimes trillions of functions with trillions of parameters that are trained based on huge amount of text data. And a benefit of LLMs is that they can be trained in an unsupervised way. So in regular machine learning, we had to create a data set with inputs and the true outputs, like the labels. So someone, like a human, had to manually label this data, right? But in LLMs, we don't have to do that because we can just dump text without annotating anything, and they will figure out the patterns. So I believe this is one of the reasons why they grew up so fast, because they are very computationally expensive to train, but in terms of data, it's much easier to just scrape websites or anything to just dump data. But making interpretable LLMs is actually technically impossible, because an interpretable model, in the end, it has to be a model where the rules can be directly seen and understood by humans. So for instance, in this example, the author was trying to predict his level of grumpiness. And then when he plotted it against the hours of sleep he had the previous night, he could very smoothly fit a linear function. So if we see this chart, it's pretty understandable to us, right? If he slept more, he was less grumpy. And then if he barely slept, then his grumpiness was off the charts. This is interpretable, just a linear function. But in LLMs, we don't have one linear function. We have, as we saw, billions of nonlinear functions, which are already one nonlinear function might be interpretable, but not quite. But yeah, we have billions of these functions. Also, the knowledge in LLMs is not localized. It's not like, let's say we have all of these functions, but maybe this group of functions here in the architecture are storing the data from Stack Overflow posts, and then we can look at there. No, it's just that the parameters of the functions were tuned based on the training data, but the training data is not stored anywhere in the LLM. So when the LLM generates an answer, it cannot really trace it back to the training data. But this is not the only challenge that we have with LLMs and explainability. Another one is their generative nature. So in regular machine learning, so in regular software, for the same identical input, we always get the same output. And that's not the case for LLMs. A disclaimer that now in many services, we can choose they call it the temperature. So we can technically make it more deterministic. But in general, if we just use it with the default values, we know that for the same query, we might get a different answer. Another challenge is that we've started to humanize LLMs. So LLMs, again, can learn patterns, so they can actually learn patterns from human interactions that were present in the training data. And they can emulate communication styles to be maybe more persuasive, friendly, empathetic. In fact, there was this research paper I read in Nature where they were studying this LLM-based chatbot, and it was like a healthcare chatbot. And the patients from the user study, they reported the chatbot to be more empathetic than their actual doctors. Even OpenAI has expressed concerns about users maybe getting too emotionally attached to ChatGPT after they released the voice mode. So this is one thing. And the other one is their overconfidence. So I think all of us are familiar with this. Same as they can learn human interaction patterns from data, they can learn patterns of expressing confidence. So even when we prompt them for their level of confidence when generating an answer, because in the end, as we saw before, they're generating word after word, so there was some probability of that word being there. So yeah, even if we prompt them for this sort of probability or like confidence level, they're not going to tell us, right? Like, they're still going to answer like in a confident way. Also, when we know that the answer is incorrect, now it's true that if we tell them, they are always like, yeah, I'm sorry, this is the right answer. But then again, they will give the second answer. Maybe it's also wrong, but they will give it with the same level of confidence. So these last two problems, the overconfidence and the humanization of LLMs, have led to overtrust and the so-called problem of over-reliance. So we tend to, like we assume that the outputs are correct from LLMs because we tend to trust them just because of the way of expressing themselves. Most companies know this, and they have, of course, expressed concerns about it, but still they have kept using LLMs and implementing them in their projects, which, when done internally, it might be okay. Like, worst case scenario, maybe the productivity goes lower because the outputs are wrong, so the employees have to correct that. But when done in a user-facing application, let's say, it can be really dangerous. There have been a lot of examples of this in the media, but well, this was one of them from an airline in Canada, where they released an LLM-based chatbot, and a customer asked something to the chatbot, and the answer was wrong. The correct answer was in the website, but this customer only checked, only spoke with the chatbot. And they actually went to court about this, and the customer won. Another example, maybe this rings a bell to some of you, but it was this lawyer in the US who used ChatGPT to generate a legal brief for a case. And all the 3 example cases that he gave, they were completely made up. And in this article, they mentioned the lawyer did ask ChatGPT whether one of the cases was real, but was happy enough when ChatGPT said yes. And he didn't do any checking outside of ChatGPT. So we should, of course, realize that LLMs are, just a tool. They're not like some magical sentient expert in any kind of field. And also that if an LLM gives a wrong answer, people are not going to blame the LLM. They're either going to blame the company behind the service, like in the case of the airline, or they're going to blame the human who used the output, like in the case of the lawyer. And explainability can help us with this, right? With being more critical about the output of an LLM, or at least more prone to verify the source, right? The information. Okay, so how can we actually implement explainable AI in LLMs? Let's say that for our project, the project I talked about before, for the blood testing lab, let's say that instead of training a machine learning model, we decide to use an LLM. So we might give it a prompt similar to this, telling the LLM that they're now a cardiologist specialized in thrombosis, and they have to predict the probability of a patient suffering severe bleeding in the next 3 weeks based on the blood test results of the patient. So in this case, we would give this prompt. Maybe we would give some examples, right, of input and expected output. And then we could start, we could start using the LLM as sort of model. So for this, we could just give all our inputs, then generate an output, or the LLM would generate an output, and then with this data, we can implement any of the classic explainable AI techniques, like feature importance or LLM, etc. But we don't really use LLMs this way, right? We let's think like, for instance, the 2 examples we just saw. Like we had a chatbot from an airline to which a user maybe asked, can I fly with my cabin luggage for free, right? And the chatbot says yes. So I totally get why we would like to overtrust the chatbot on this one. I don't like to pay for my cabin luggage either. But still, it's not like the LLM is going behind the scenes. If we take into account the number of tickets sold for your flight and the number of pieces of checked-in luggage there are, and whatever, like the level of friendliness of the crew for this flight, there's an 80% probability that you can get your cabin luggage for free. No, mean, we asked that question because it is stated somewhere in the airline policy. And yeah, we just want to know that, right? And same goes for the legal case, like the lawyer case, right? If we open ChatGPT and we ask, am I allowed to fly from, I'll say like Amsterdam to Copenhagen and bring my cabin luggage for free? And ChatGPT says yes. Like, okay, that's fine, but that's not really enough for us, right? Like, I would maybe like to see the article from the European Parliament where it is now stated that EU passengers should be allowed to bring cabin luggage for free. So then when I arrive to the airport and they tell me you have to pay for your cabin luggage, I can like show them this and not just say, yeah, ChatGPT told me that. So what these two cases have in common is that we are not using the LLM as a predictive model, but we are using it as an information retrieval model. Maybe we want to find specific information that we don't know where to look for it, or maybe we're just too lazy to Google it, you know. But in either case, we want to know if what the LLM is saying is true or not. Like in the end, we want to know where it took this data from, right? So in the early stages of LLMs, this wasn't really possible. So as we saw, LLMs are, generative models that just predict word after word based on like some parameters that were tuned during training, but it doesn't have any access whatsoever to the training data anymore. So yeah, in theory, we wouldn't be able to explain this, right? That was until RAG came along last year, like a couple of years ago. How many of you know what RAG is? If you could raise your hand. Okay, a few, but not everyone. It was just to know if I should explain or not, but I'll explain very quickly. So RAG system, well, it stands for Retrieval Augmented Generation. And it's this idea of combining generative model, so the LLM, with an information retrieval component. So how it works is that instead of just writing our query to the LLM and it generating an answer, behind the scenes there's some database, we will call it the RAG database, and then we ask our query, the retrieval component finds the most relevant document or documents for this query, retrieves them, and then this plus our query are sent into the LLM. So the LLM is generating an answer based on this like contextual information coming from the documents. And RAG has been pretty useful, and now I think it's used in most LLM services, because training LLMs is really expensive, as you know, like computationally and time and money-wise. But not retraining them can also be very expensive because they can be outdated quite fast. So something like RAG allows us to, enhance the data that's used by the LLM without having to retrain. And with RAG, we can actually implement probably the most known, like popular, explainable AI technique for LLMs, which is source attribution. You've probably seen this already. Most known services, like Microsoft Copilot or ChatGPT, they already implement this. And source attribution can be implemented like in its baseline form, so just like outputting the LLM answer and giving you the sources by simply adding metadata in the RAG database. So if in the database we store not only documents, but also metadata containing the title, the author, maybe the URL to the source, then when the LLM answer is given to the user, in addition to that, we can give the metadata of the documents, just as easy, right? So then the user can actually see what the sources are. But ideally, we want this, and we would also like inline citations, right? Like we would like to know which parts of the answer came from which document. So I don't know exactly how Microsoft or OpenAI implement this, but most research methods work in this way, so I'm assuming they work in a similar way. So I'll explain it just with an example. It's a bit of a silly example, but just so that it's clear. So let's say that we ask an LLM something like this, right? When was .NET 9 maybe released? How can I install it? And then it gives us this answer with like the date of the release date, and then yeah, that you can get the installer on this page and just follow the steps there. And then it gives us two sources, and one is from the Microsoft Learn, and the other one is from the official .NET documentation. So what the LLM or like RAG system would do behind the scenes if it has citations is, before giving this output to the user, it will remove one of the documents that were retrieved, and then it will generate a new answer, like the LLM. And then all the words, like all the tokens that are missing in the new answer that were present in the original answer are attributed to the document it just removed. And then it does this for every source document, so same for the other one, so that eventually it can add the inline citations. So I know this, if we see it like this, it sounds a bit convoluted, but again, like LLMs are black boxes, so it's the only way, like we can only see inputs and outputs, so that's how we can, well, sort of know where each part of the answer came from. But let's say we ask the LLM something like this, and one of the source documents is like this massive document, maybe like hundreds of pages, and the answer is rephrased so much that it's impossible for us to like trace the answer back to this document. And after this session, I think all of us don't really trust LLMs so much, right? Like we already knew that they can hallucinate, so what can guarantee us that they are not hallucinating the citations, right? Like I'm pretty sure they were trained with research papers, so I think even like a 2-year-old kid could write square brackets and numbers. That seems pretty easy to just put in there. So here comes the second technique I wanted to talk about, which is scope detection. So this is basically detecting if the user query is in scope of the RAG database or not. So if we have something like this, plus the inline citations, we can be a bit more certain if the answer is reliable or not, because if the LLM or like the RAG system tells us that the query is in scope, then okay, most probably the answer was based on some source document. But if it tells us that the query is out of scope, then I don't think we should trust the answer of the LLM, or at least we cannot verify it with a source document. So the way that scope detection can be implemented, again, like this is based on reading many papers, and this is like the more like high-level explanation. Maybe it can be implemented differently, but as a general rule, the idea is to create a data set with examples of in-scope queries and out-of-scope queries. Then we have to choose a goodness of fit metric. So this is basically some like similarity score metric or like distance metric. Typically, maybe like Euclidean distance is used. I don't know how many of you have like had math at uni or anything, but so that's the idea. So we have this data set, and then the goodness of fit metric is calculated per query against the most relevant document found by the retrieval component. And with this data, we actually train a binary classifier, so another machine learning model. The accuracy of these scope detectors tends to vary a lot, depending on if the in-scope and out-of-scope queries are like closer, like similar, more similar or not. So let's say like in the previous example, if, just go back. If we ask something about .NET, and let's say we're working with a RAG database from Microsoft, and no, let's say like the one just for .NET documentation, let's say. And then we ask something about Denmark, then okay, like, do we know that the queries are very different, like they're far apart? But maybe if we ask something about, I don't know, like VS Code, it is technically an out-of-scope query because it's not related to .NET, but I'm pretty sure VS Code is mentioned in the .NET documentation. So then it's a bit of a gray area, right, if this is in scope or not. So what one of my colleagues actually did was that he implemented his own scope detection model, like technique. And instead of having a binary classifier, he used a multi-class classifier. So he had in scope, out of scope, and scope related. So this was very nice because then we can have more certainty that the in-scope queries are really like true positives, like in scope. And then for this gray area where we are not sure if they are or not, they will be predicted as scope related, hopefully, so that then we can maybe manually investigate if this is actually present in the RAG database or not. Also, as an example, I don't want to go too much into it, but for goodness of fit, he used this so-called BM25, which is like a keyword matcher. So it basically finds like how many of the words in the query are present in the retrieved document, also the frequency of these words to like determine the similarity. The problem of this is that it doesn't take into account semantic information, so it's just literally matching keywords. So if there are synonyms or anything, it cannot, doesn't measure that, which is why he also used the dense embedding distance, which is again like the distance between queries or like tokens in the embedding space. So I don't want this to become like a full-on workshop about LLMs, but yeah, that's more or less the idea. So he did like a weighted metric between these two. So in enterprise AI systems based on LLMs, actually out-of-scope queries account for 10% of the errors, apparently, like according to some auditor company study I read. And with scope detection, if we implement this, and if we implement maybe like a RAG system where in the database we only have like custom verified data, right? So we only store data that we know is truthful, let's say. And we force the system to only answer in scope queries, then we can already be more certain that the answer is correct. Of course, we can also combine it with the inline citations and maybe force the system to only give citations for in-scope queries, because again, if we get citations for out-of-scope queries, then it's most probably hallucinations. Okay, but let's say that we don't want to implement our own LLM or like our own RAG system, right? We just want to use whatever's there out of the box. We saw before most like well-known LLM services, they already implement at least source attribution and inline citations. Microsoft Copilot, ChatGPT, Bing Search, Perplexity. Sorry, but let's say we want to use another service that's not one of these, and that maybe doesn't implement source attribution. We could try self-citations, which is basically just asking the LLM for citations. As you might imagine already before this session, but especially after everything we talked about, this is probably not the best idea, because if we're lucky and the service uses a RAG system, maybe it might work if we ask something in scope. If not, then it's probably hallucinated, or maybe it's not, but maybe some sources are missing, or it's probably maybe referring to non-existent sources. But if you want to try it out, I always vouch for trying everything out. Here's one tip. So also I read this in another paper. It wasn't the goal of the paper, but it was just something interesting that I read about. So apparently, in general, for any kind of LLM, if we ask a question, we send some query, versus if we ask the same question but asking for citations, the answer tends to be more correct in the first case. So you might think, OK, then I'll just ask my question, and then afterwards I'll ask for the citations. But then the citations tend to be more incorrect than if we ask for both combined, which kind of sucks. But my recommendation would be, if you want to try this, not the best idea, but if you do, just try both, see the outputs. If they are similar, then it looks promising, right? Maybe it actually gave the right answer. If they're not the same answer, then maybe we should just look for the information ourselves, or maybe double check it. And in general, in either case, if both answers are correct, just don't trust it already. Double check your sources. Don't be the US lawyer, right? So I said before that we mostly use LLMs as a sort of smart search engine, right? Like to retrieve information. But we also often may want them to perform some task, especially nowadays with the whole like agentic AI hype and everything. Yeah, LLMs are they started being used to fulfill certain tasks. And in these cases, maybe source attribution could be useful, but maybe it's not enough because we want to know how the LLM arrived to a certain answer. Maybe it's not, something that was retrieved from the data. So again, the most, naive option would be to ask the LLM for explanations. And again, you might be thinking, okay, we saw LLMs can hallucinate their answers, so they can for sure hallucinate their explanations. And that's correct. Even if the LLM manages to generate explanations, they might not be matching the logic that it used to solve a task. But still, like having these explanations or like asking for them can be useful because it at least allows us to verify the output, like does the explanation make sense or like match the answer or the problem? And if not, at least we can, decide to maybe redo the prompt, reiterate, and try something else. The problem with this is that, well, if we want the LLM to perform some task, it can only really work if that task or like the process to do that task was present in the training data, because then maybe it can like replicate it as it is. If not, then yeah, we don't have as much certainty. Again, like LLMs just generate word after word. So the more complex and multi-step processes or a task is, the higher the chance that the answer will be wrong, because the lower the chance that this process was in the data, in the training data, or the RAG database. And also, the longer that an answer from an LLM is, the higher the chance that there will be some wrong word predicted, right? I mean, the more words we have, the higher the chance that one of them is wrong. And then if one of the words is wrong, it will probably cause a snowball effect of generating the wrong words after that. So, yeah. So in these situations, if we want the LLM to perform some more complex task, it is useful to break down our prompt into a series of smaller, simpler tasks or prompts. You maybe heard about this technique before. It's called prompt chaining. And yeah, it's pretty well known for, actually improving the performance of LLMs for problem solving. It's also much more flexible because then we can tweak like each prompt separately. But it also gives us more transparency because we are getting the output per like subtask. So if there's a problem in the process, we are gonna be able to exactly like pinpoint where the problem is and maybe like redo that prompt or anything. Whereas if we just have one big prompt and we get the wrong answer at the end, we don't know where in the process it went wrong, right? So, well, this is just an example of how it would work. Maybe like, let's say we have some research paper with a list of explainable AI methods for LLMs, and we ask the LLM, like based on this document, generate a summary, and then we use the summary in the next prompt to we ask it to write like an intro, body, conclusion for a presentation about this topic based on this content, and then we get the draft for the presentation, and we dump it again onto another prompt and ask maybe like to redo this, like write it in a more professional tone, maybe put like some jokes here and there so that people are, that you keep the interest of the audience. This is, of course, totally not how I created this presentation, by the way. It's just an example. There is a way, however, to get a similar performance when prompting, but just using one prompt. And it's called chain of thought. So it's a sort of improved version of few-shot learning, right? When we give the LLM like some examples of inputs and the output we expect, so that it can normally generate the output, like perform a bit better when generating the output. So it's the same idea, but in addition to the like an example input and an example output, we give an sort of high-level description or an example on the process to get to that answer. And this apparently, well, improves performance quite a bit, even for, simple like primary school math problems. Just don't use LLMs for math problems. We just saw they just generate words. They're never gonna, even when the answer is correct, it's just, they happen to generate the right number, right? So, I mean, not the best example, but it was the example in the paper, so yeah, it actually worked. There are a lot of variations of this chain of thought technique. One of them is called tree of thought. So it's basically the same thing, but we provide a more detailed step-by-step explanation on the process to get the answer. So also like with conditions and branches. So it's a bit more similar to the human decision-making process, right? I mean, I'm just showing this to you so that you know what's out there, but I mean, my personal opinion, okay, if some of these tasks are related to generating text, okay, like let's try them out, but at some point, like, this problem, if you know how the process is to arrive to an answer, just write the code, right? Like, I don't know why we want to use LLMs, but yeah, if you ever think of a use case where you don't have to make calculations, but generate some text, this actually performs quite well. And in fact, for tree of thoughts, in the paper, they have several different example, like use cases. This one I found it pretty nice because they managed to solve crosswords puzzles with it. So the LLM was like generating words to fit in the crosswords, and then whenever it reached a point where they couldn't generate a word that fitted with a definition and the boxes, then it will like retrace and generate another word for the previous step and so on. So yeah, it's pretty nice. Just I don't see the point of using an LLM to solve crosswords, but it's a nice gimmick, right? Okay, so let's say that we try these techniques, some of them, and we end up with the best possible explanations for our LLM use case. But if the actual output, like the answer of the LLM, is incorrect, then this is pretty useless, right? So my advice would be just use the general good prompting practices, let's say, or like prompt design. Use simple, concise language, be direct. Don't be too polite. Like this used to be a thing that if you were very polite, you got like better results. This is not the case anymore. Apparently, there was also like a research paper about it for newer, like bigger English, mainly English models. Politeness doesn't really improve the performance, but still, like don't be too rude. Like if we add a please here and there, it might actually improve the answer a bit. Refine your prompts, try again. We can keep on improving both the explanations and the performance. Maybe we test a prompt, we see the output, we identify issues, and then we can retry again, maybe extending the prompt or, rephrasing it. Explore, experiment, try one of these techniques. If it's not working, try another one, maybe combine them, see the output, see what works for your query, for your project. And finally, even if we end up with the most optimal prompts and the best, most correct answers and best explanations and everything, these, like the LLM output and the explanations, they shouldn't be directly used. Like there has to be some human validation on, like a large enough data set before any like LLM-based product or output is used at a large scale or, in a user-facing application. And even though we're currently in the middle of this agentic AI era, hype, whatever, for high-risk applications, so again, we saw high-risk is basically any AI application nowadays, the LLMs should act as an assistant to an expert human, right? Like, they should never take decisions on their own, ideally, because do we really want, like smart, like fancy word predictors to make decisions for us? Well, thank you very much for joining me today. And if you have any questions, let me know. Yeah, also feel free to connect with me on LinkedIn if you want to talk about this or you have any question that pops up later tonight. I'm also going to be here until Friday, so just feel free to come by.